So in this video, I'm going to talk about the BJT small signal equivalence models. So I wish to upload the video series in this case. So, uh, so it is actually, this is chapter 1, and let's begin. So you can see that in this case, there is a small signal voltage source and the bias voltage source. The capital VBE denotes as the bias voltage source, and the simple VBE will denote as a small signal voltage source. So this is the actually this current will be the overall base current, and this current will be the overall collector current, and this one will be the overall ammeter current. Actually, this overall currents are equal to the small signal ammeter current plus bias ammeter current. So the addition of these both two is equal to the small signal ammeter current. Okay. So actually this circuit is known as this circuit is known as the conceptual circuit. So why is this circuit is known as a conceptual circuit? Because you can see that these voltage sources are directly connected to the base terminal. So that's why this kind of the circuit is known as a conceptual circuit. But in the practically, we do not connect these voltage sources directly to the base terminal. Instead of that, we usually use the resistor. So we usually use the resistor. But in this case, we are connecting these voltage sources directly to the base terminal. So that's why this kind of circuit is known as a conceptual circuit. Okay, this kind of circuit is known as a conceptual circuit. So how can we draw the small signal bias circuit using this conceptual circuit? So to draw the small signal bias circuit, in this case, what we want to do, we short circuited of the small signal sources. Okay, we short circuited of the small signal sources, and but the bias voltages we keep as it is, and also this is the bias voltages, and this is the another bias voltages. We bias voltages keep as it is, but the base, this is the small signal voltage sources. We short circuited these small signal voltage sources, but the bias voltage sources keep as it is. Then we can get the small signal equivalent circuit like this. So this is this is the bias circuit. Okay, so then we can get the bias circuit like this. So actually this one is called as a bias circuit. Okay, these are the bias circuit relevant to this. Okay, this is the bias circuit. So how can we get the small signal equivalent circuit using this conceptual transistor circuit? So to get the small signal equivalent circuit, what we want to do, we short circuited the bias voltage sources. Okay, we short circuited of the bias voltage sources, and this voltage sources we connected to the ground. Okay, we connected to the ground. From that we can obtain the small signal equivalent model. So the small signal equivalent model will be like this. Okay, so this is the, you can see that this small signal voltage source is transferred to the this side, and the bias base to emitter voltage is short circuited. Then this VCC is removed and connected to the ground. So this is something like a small signal equivalent circuit. Okay, so you can see that these are 5. So the current of the IB, again small signal base current, is equal to the VBE divided by R5. So the R5 is the known as the resistor seen by the input. Okay, the resistor seen by the input, and this is IE is a emitter current, and this is IC is collector, small signal collector current, which is determined by the GM times VBE. GM is known as a transconductance. Okay, and the RE. So how can we determine the RE? Actually, the RE is equal to the, so this RE, actually this RE is used for the to design the T model. Actually, we discuss later chapters, and actually this RE is equal to the alpha over GM. Okay, the alpha over GM. Let's begin with the hybrid phi model. In the hybrid phi model, we can use the this kind of R phi resistor and the dependent voltage current source. Okay, this is a dependent current source. R phi resistor. This is something like an input resistor, and the dependent current source. The dependent current source is a GM times VBE. So this is known as a hybrid phi model. So in which case, so you if you have a question, what kind of scenario do we want to use this hybrid phi model? Actually, if you think about this circuit in the previous slide, in this circuit, you can see that there is no resistor in the emitter terminal. Okay, so in this kind of circuit, we can directly use this kind of hybrid pi models. But if you have the resistor in the emitter terminal, imagine if you have the resistor in the emitter terminal, if you have the resistor R capital E resistor in the emitter terminal, you cannot use the, actually you can use the hybrid pi model, but there is a difficulty when you are in the calculating. But so to easiness, we in this kind of scenarios, we can use the T model. So if you have the, remember that if you have the resistor in the emitter terminal, we can use the, frequently we can use the T model. Otherwise, we can go with the hybrid pi model. In this, so in these scenarios, so these are the elements or the characteristics we know about to this kind of calculations. So we know about the transconductance, input resistance, and this is a dependent current source. So these kind of things, these three, this one and R5 and AB node. So these three are dependent on the bias circuit. Okay, these three are dependent on the bias circuit. Okay, so if you want to calculate the transconductance, input resistance, and the open circuit voltage gain, we use the bias circuit to calculate these kind of characteristics. So if you want to determine the R5, actually we go with the bias circuit, not the small signal equivalent circuit, because these are the bias current, and this VT is actually the thermal voltage. Okay, this VT is thermal voltage, and So actually these three things, these three characteristics we need to determine by using the bias circuit. Okay. And other than that, so we know the IC, collector current. The bias collector current is equal to the beta times IB. Beta means uh, the beta times IB. So the beta means the common emitter current gain. Okay. So it is simple equation. I think you know that is a simple scenario and simple relationship, and so we can replace this dependent current source by beta times IB d beta times IB like this. So this is, so this circuit or this circuit we can use the according we can use either this circuit or this circuit according to our calculations. Okay. Then we can try about this example. So you can say that this is the we are, so we need to imagine we need to determine the small signal equivalent circuit. So this is very complex scenario, and you, so this one, actually this one is the bias circuit. Okay, this one is the bias circuit. Okay, so these capacitors, actually these capacitors are called as the uh, coupling capacitors. Okay, these capacitors are called as the coupling capacitors. Actually this capacitor is known as a bypass capacitors. Okay, this capacitor is known as a bypass capacitors. So the coupling, what are the uses of these coupling capacitors? Actually the coupling capacitors used for the, it actually the coupling capacitors, it blocks the DC signals, but it pass only the AC signal. Okay, it pass the AC signal, but it blocks the DC signal. So actually this coupling capacitors is used for the to keep the bias point. Okay, to keep the bias point of this transistor as a constant. So that's why we use this kind of coupling capacitors. But so what are the purpose of using this kind of bypass capacitors? Actually the bypass capacitors is used for the to ground any kind of unwanted AC signals. We need to use these kind of bypass capacitors. Okay, this kind of bypass capacitors. So next thing is, how can we draw the hybrid pi model? In the hybrid pi model, we assume these capacitors are act like a perfectly short circuited for the something like a high frequency signal. So that means these capacitors are act like a perfectly short circuit. So that means we need to neglect this resistor. Okay, we can neglect this RE resistor because this one is the short circuited. The current is going through this path, and this path. Okay, then we can draw the hybrid pi model like this, and this is the ground, and this is the base and emitter. This is the input resistance R5, and there is a two resistors. Okay, this is the only one resistor. This is actually the RB1, and this is the another resistor. This is called as the RB2. And this is the dependent current source, and this is actually the GM times VBE, and and there is a RC resistor connected to the ground because we interested in the small signal equivalent circuit, not the bias circuit, and there is a RL, the load resistor. Okay, RC and the RL, and we output the voltage from this terminal. This is our output. Okay, and in this case there is another resistor, the resistance of the signal voltage source, we can say RC, and there is a signal source like this. This is our signal source, small signal voltage source. So this is the actually this is something like a complex circuit. If you can draw like this kind of circuit, you can easily draw another circuit very easily. So this is the circuit we need to interested in. This is actually the base terminal, emitter terminal, and this one is the collector terminal. This is the collector terminal, base, and the emitter terminal. Emitter terminal is grounded because this is the emitter terminal. We can neglect these resistors because we assume the signal frequency, the frequency of the signal voltage is considerably high voltage, and this RB1 is resistor is coming to this terminal, and RB2, this RB2 resistor is coming to this terminal, and this VCC is connected to the ground, and this RL is coming to this, and RC is coming to this. This is actually the small signal equivalent circuit. So this is the very clear image of the small signal equivalent circuit. So you might be wonder what are these arrows. Okay, these arrows is represent, this arrow is represent the input resistance. So the input resistance, actually the R5, this RB1, RB2 are parallel. Okay, so you can see that this R in resistance is get this kind of equation, and the VI means the voltage of this terminal. So this using the simple relationship, we can use the we can get the input voltage like this, and also we can use the output resistance. So the output resistance is, you can see that if you look at this R0 and the RC are in the parallel. Okay, this is actually the output resistance. So output voltage is, this is the current going through this terminal. Okay, this is the current GM, and R5, this is the current, and this is the current going through this circuit, because, and we consider the current is going through this one, but we consider the voltage drop in this direction. So that's why there is a minus comes here. So this is the current GM. The R5, actually this one is GMVBE. Okay, GMVBE, and RC parallel, RL parallel R0, because these three resistors are in the parallel combination. That's why we can use this circuit. Okay, so from this example we can calculate the overall voltage gain. So this is the equation we can use to calculate the overall voltage gain. So this is the input resistance. Overall voltage gain is V out divided by V sing. Okay, so from that equations we can get the, from that equation, this kind of equation, this from these equations we can get easily to the expression to the small signal overall voltage gain. Okay, this is the overall voltage gain, and actually this is the end of the uh, video, and the next video will be the T module. So stay tuned. Thank you for the listening.